Okay. So this takes care of a huge issue that you have to think about. Either changing your matrix or think about changing your Fourier transform. Okay? Now, let's come back to this problem here. And let's think about how. So now we've been talking about the stream function solve. We've been talking about simply this, right? How do we find this stream function? That's where the bulk of computation will happen. This is where you have all these problems with infinite number of solutions, everything. Now, what I'm going to show you is that this problem here, which looks harder, doesn't it kind of look harder? Like you got like all kinds of terms. You have time dynamics and space dynamics. This is easy. All this is matrix multiplications. This is actually solving a large n by n system. This is just multiplying matrices. So let's see how this works. Okay, so let me erase here. So first of all, what we did find is that this Laplacian operator, which is 2 derivatives in x, 2 derivatives y, is equivalent to a matrix A. Right? So the matrix A does this for you. So when I think about starting to represent this thing now in a MATLAB way, let me first of all think omega t is equal to nu del squared omega minus psi x omega y plus psi y omega x. And now when we think about putting this stuff in terms of vectors, because that's what we want to do, then this becomes, and remember how we arranged the data? We stacked it all. We took this two-dimensional thing, remember, and we took data and we started counting from here, going up. So we had omega is equal to omega 1, 1, omega 1, 2, omega 1, 3, and then omega 2, 1. That's how we arranged the data. And so we'd have this is equal to nu times that del squared is just that. It's a matrix multiply. And the claim is here that these guys, well, these guys are easy. Because what they are is minus psi of x. Well, there's an x derivative. And let's think we can construct a B matrix that does an x derivative and a C matrix that does a y derivative. Then this becomes B times psi times C times omega. See that? Plus C times vector psi times B times omega. That's it. So this is your right-hand side. This is what you put into OD45. You can do this whole thing with one line. All it is matrix multiplies. Okay? So even though it looks like the harder part of the problem, in OD45, one line. Multiply this by this vector, this by this vector, this by this. Put them all together. Got your right-hand side. The only thing we need to think about is how do you construct B and C now? Okay? We know how to do A. We spent a lecture on that. Let's talk a little bit about how to do B, and then you're going to have to do C. Okay? All right. So everybody good with that? That's it. So notice there's no problems. If that matrix A is singular here, who cares? You can multiply a singular matrix by a vector. There's no problems with that. There's no problems with any of these matrices being singular. Only when you try to do the stream function solve, right, where you're solving an n by n system. Here you're not solving an n by n system. You're just saying, take what the values I have, multiply it by some stuff, get a new value. Okay? So let's talk about the matrix B. And in homework, you'll have to, I'll show you what it looks like. Then you guys have to make the matrix C. And then you have to make them all on MATLAB. So we'll talk about how to make these on MATLAB tomorrow. Okay, so first of all, let me draw my grid. Blah, blah, blah. So here I have, how did I count before? These are x and y. And this was omega 1, 1, omega 1, 2, omega 1, 3. And then this was omega 2, 1, omega 2, 2. And remember how I stacked information. What I stacked information was like the following. Omega 1, 1, omega 1, 2, omega 1, 3, all the way up to omega 1, n. And omega 2, 1, omega 2, 2, all the way to omega 2, n. And then omega n1, omega n2, all the way to omega n. So we're going to cut it up like a square. Actually, that's my n plus first point, and my nth point is here. Let's talk about why I have n plus 1 points. Because remember, it's periodic boundaries. So we're going to start building the B matrix. So we're going to build B times omega. We want to differentiate in x. Remember your differentiation formula? Point in front minus point behind all over 2 delta x. Comes from the tables. So that's what we just have to think about. We're going to just do this here. So first of all, I have that 1 over 2 delta x. Let's just go ahead and take that out front. Don't forget those, by the way. Yeah?
So the other one, was that the same? This is like a order.
Yeah, this is order delta x squared scheme. Yeah.
And the other one was delta x squared too.
That's right. Yeah, that's right. But there were 2 derivatives in x and 2 derivatives in y. And now we're just doing 1 derivative in x. And so we have this. And let's go through and let's ask about this guy right here. Omega 1, 1 cares about who? 2 neighbors in the x direction. Here's one of the neighbors. The other one is over here somewhere. You kind of go, well, there's no neighbor. Well, you do have a neighbor over there because it's periodic boundary. So this point is the same as this. The neighbor of this one is this one. So what does that mean? Well, I rely on omega 2, 1. Where's omega 2, 1 on this list? It's n away. So if I think about n components here, n components there, n away, there's a 1 over there. That's the point in, shoot. No, sorry. Minus 1, right? Let me make sure I got this right. Yeah, so, oh, actually, my point in front is over there, point behind is over there, the way I think about this here. So, right, there's my point in front, there's my point behind, so I have a 1 right there. The point behind is over here, which is n1. Where's n1? Way down here. So these are little n by n matrices within this big. Remember, this whole thing is n squared by n squared. And then these are all little sub n by n matrices within it. What about this guy? Who are its neighbors? This one and this one. Okay, so what's that one? Omega 2, 2. Well, that's 1 over from omega 2, 1. And then this one here goes to the next one. See a pattern? Me too. Start getting 1s down here, here. And then let's go, okay, so what happens here? Well, what happens there is we got to the end, now we come back down here. Now we go to omega 2, 1. Omega 2, 1 is this guy. Who are the neighbors of omega 2, 1? This guy here, which is omega 3, 1, minus omega 1, 1. Well, omega 3, 1, that's there. And then omega 1, 1, that's there. And then the next one up, omega 3, 2, lies on this and this. And all of a sudden you see there's this pattern. And by the way, when this hits the edge here, where do you think it goes? 4 diagonals. 1, negative 1, 1, negative 1. Everything else is 0 in this matrix. That takes an x derivative for you, the way we have the data arranged. Okay? All right. So now, another way to represent that matrix. Okay, so this is what you're going to have to do for the y derivative. You're going to have to draw that little chart. And you say, if I do a y derivative, it's this guy and that guy. And then this guy, these two. This guy, these two. You have to do something similar. It's going to look different. Okay? Okay. So now, what does it look like in sort of in some more sophisticated way of thinking about it? The B matrix looks like the following. You have these identity matrices. And then you have these minus identity. So it's like on a bigger structure, each one of these identity matrices are these blocks, and these blocks run on the off-diagonal blocks and then on the corners. So that's what your matrix B will look like. Okay? This takes a derivative in x. By the way, once you construct the C matrix, right? You have a C matrix that takes the y derivatives, B matrix that takes the x derivatives. You could say, hey, if I wanted to come back over to this problem, I don't really need A here. I could do the B matrix squared plus C matrix squared, right? B squared plus C squared, right? Because B squared is 2 derivatives in x, plus C squared is 2 derivatives in y. But that's kind of dumb. And here's why it's dumb a little bit. You might construct it outside the loop, and that's okay. But if you do it inside the loop, it's dumb. This is going to be sitting in OD45. And what you're going to be doing is keep every little delta t step you take, you're going to call on this thing 4 times to evaluate. You do not want to be doing huge matrix multiplies in here. You want to be doing this as fast as you possibly can. So you construct the matrix A once and for all. So it's one matrix multiply. Don't make this B squared plus C squared times this, because then it has to go in there and go, okay, you want me to square B? Okay, I got it. Plus square C. I got it. Now make the multiply. Even if B and C are sparse. You're still doing extra work. Whereas if you do it ahead of time, you've saved yourself 4 matrix multiplications. Okay? Because you have to do square plus square, and then the adding, too. So 4 matrix multiplies plus adding. Actually, no, sorry. 2 matrix multiplies plus an addition. You've saved yourself that much work.
But B squared plus C squared equals A modulo that one with a tweak.
That's right.
I mean, you would get the same result if you
Yeah.
just matrices did it, and then make it yourself.
Almost. I haven't talked about it yet, but you get modulo something on the diagonal. Modulo a constant, actually. Okay.
That one little constant? Or the
No, the whole thing, the whole diagonal. Yeah. So anyway, that's how you think about doing this. Is that making sense? That's how you scale the problem up. And by the way, B and C themselves are singular. You don't care. You're not doing a backslash. You're not trying to solve for an n by n system. All you're doing with B and C and A, in this case, to solve for the vorticity, is a matrix multiply with matrices that are mostly empty. And so your job is then to construct those matrices. So let me tell you about homework.